Hello everyone. Welcome to in this session. And in this session, I will be discussing about the control system under the initiative of the your own teacher. And we provide like the project guidance and the doubt clearing session on related to all undergraduate and the postgraduate subjects. So let us go into this course structure. So the control system, if you look into this control system is taught on the both on the undergraduate level and the postgraduate level. So the level of the study will be different on the undergraduate level and the postgraduate level, but this is the whole thing which is covered under the control system course. So the control system course, we will be discussing about the control systems. If you look into surroundings of your system, there will be a lots of system which we will be controlling. So anything which have any control type of thing is known as the control system. So if you look into the control system, then this is the general structure of the control system. If you look into that, we have some kind of input to the system. So let us suppose we have a system. If you have, you can one take some general example, then you can take an example of fan. Then suppose we have some kind of input. So if you take the example of any control system, then if we talk about the what will be there in the control system, then we have some kind of input, we have some kind of output, and we have some kind of plant. So if you see this process, including the connecting lines, is known as the plant. So if you suppose this is the like core part of our control system, so this will be the plant. It is known as a system on which we will be performing the control. And there will be some kind of controller by which we can control the input to the plant. So if you look into the general structure, then we have a control input, we have some kind of controller, we have some kind of plant, we have some kind of output, and we have some kind of feedback controller also. So these elements make a control system. You may have some element missing in your control system. On the basis of you will be defining the various kind of control system, like you don't have, sometime you didn't have the controller in that system, then you will be having some kind of control system like that. And if you have don't have this feedback feedback path, then you will be having the open loop control system. If you have this feedback path, then you have the closed loop control system. And on the basis of this comparator, where the this feedback signal and this input signal are subtracted or added, on the basis of that we will be having the type of the feedback. Like if both the signal are added here, then it is known as the positive feedback, and if those signal are subtracted here, then it is known as the negative feedback. So this is the general structure of the control system, which will be having such kind of element. You have some kind of disturbance also in that, then it will be having in the plant. So maybe sometimes there will be some kind of disturbance also there. So if you take the example of fan, then suppose like we are controlling the fan by some kind of regulator, then we will be giving the supply to the regulator, and that regulator will be generating some kind of input for that fan, and it will be giving some output. So the speed of the fan, if you take as a output, then you will be giving the electrical signal to the controller, and you will be getting the speed on the as a output of the fan. So this is the kind of general control system. If you want to take some example, and if you want to take the example of the like closed loop control system, then you have to take the example of a motor, which is which speed is sensed by some kind of speed sensor and fed back to you, fed back to the this detector. So if you take like if you put a motor in the place of this control system, then suppose there is some kind of controller by which the supply is fed to the motor, then you will be giving some electrical signal to this comparator, and this speed sensor will sensing the that speed from this, and it will be converting it to the electrical signal, and both electrical signal is compared over here on by this detector, and that error signal will be surpassed to the controller, and on the basis of that error signal it will be generating the input for this motor. So this is kind of closed loop control system and open loop control system. So normally we use the closed loop system are more accurate, because here we have some kind of sensing element also there, so that we can, if we require some kind of specific kind of output over there, then we can feed the same output from there, and you will be getting the same output from here by this control element. So this is how a control action performs. Like if you need some kind of speed, like if you want to motor to run on 1000 rpm speed, then you have to give 1000 rpm from there, and you will be getting exactly 1000 speed on this output of the motor if you have designed the control system in perfect manner. So if you feed 1000 from there, and you will be getting some kind of speed here, and on the basis of this speed, there will be some error generation by this comparator, and that error will be feeding to the controller, and that controller will be generating the input signal for this plant. So this is how control action perform in the control system. So this is all about the controller, any control system general structure. So let us move toward the basic structure of the course. So if you look on the undergraduate or the postgraduate level, then you will be finding these topics will be there in the general control system. So first topic which will be covered under this control system course is the basic of the control system. So in this basic of the control system, we will be discussing about the various type of the control system which are there in the like our surroundings. So if you talk about the type of the system, then you may have like motors, various kind of like generator, or if you are from the electrical background, then you will be getting like a lots of electrical elements, which is known as a system. So in the basic of the control system, we will be discussing about the various kind of system which are presented around us. Okay, so after that, in the basics, we will be trying to model those systems, because to do the analysis kind of thing in the control system, we have to model all those systems into the in a predefined method. Like if you have any control like electrical system, then you will be modeling it into the like control system form, and you will be representing all those things in this form, in which we have some kind of input, some kind of system which is having some kind of transfer function. So we will be representing all those things by their like Laplace transform, and those Laplace transform we will be representing all by these things. So in the modeling part, we will be modeling all those systems into the control system format. Like if you have any electrical system or any mechanical system, then we will be modeling all those things into the transfer function form, by which we can correlate the input and output relation of for that system. And along with this input output relation, like modeling of the system, along with that, we will be also doing the like calculation of the transfer function from that. So we have a lots of kind of things, like we have block diagram representation of the control system. So we can we have some kind of numerical in that, also in the block diagram reduction, by which we can find out the transfer function of that block diagram. So in the such kind of system, you will be having some complex kind of block diagram, and you have to find out the transfer function of the system. So you have to apply the block diagram reduction law, and you have to find out the final transfer function, like input output relation for that system. Along with that block diagram reduction, you may have find sometimes that Mason gain formula for calculating the transfer function of the system. So for that, you have to convert the block diagram of the system into the signal flow graph. So there will be a conversion strategy by which we can convert the block diagram of a system into the signal flow graph, and after that we can apply the Mason gain formula to find out the final transfer function of the system. So after that, the basic of the control system, maybe we have some kind of like Laplace transform also covered under the basic of the control system. So sometimes we read Laplace transform as a separate chapter. So in the Laplace transform, what we will be doing, we have some, let us suppose we have some kind of time domain signal. So in the Laplace transform, by the Laplace transform, it is a very important tool by which we can convert the electrical domain signal into the time domain. So electrical domain quantity are converted to the time frequency domain by the Laplace transform. So Laplace transform, if you want to define this one, so it is a very much important tool for the conversion of the time domain quantity into the frequency domain quantity. So if we have some like variable in the time domains as a t, small t, then we will be getting the small s, that is frequency, in the after the Laplace transform. So under the Laplace transform, we will be discussing about the Laplace transform and the inverse Laplace transform. So by the Laplace transform tool, we can convert the electrical signals into the frequency domain signal, and by the inverse Laplace transform, we can convert the frequency domain signal into the time domain signal. So these are like opposite tools by which we can perform the Laplace transform and the inverse Laplace transform. So by these tools, there will be some kind of initial and final values theorem by which we can find out the like starting value and the final value of any signal. So all those things will be covered under the Laplace transform. And after that, we will be talking about the representation of the control system, like how we can represent a control system. So in this, we will be including the modeling of the control system, which we have covered into the basic of the control system, and we will try to represent the control system in a proper systematic method. Like there will be some kind of like in the systematic method of representation of the control system, if we talk about, then there will be some kind of input, some kind of output, and there will be some kind of input output relation by which we can correlate the output and the input of the system. So in this representation, we will be try to represent the control system in the proper method. So after that, a whole analysis of the control system start after these three steps, like these three steps, like basic of the control system and Laplace transform and the representation of the control system, like the proper analysis of the control system start. So let us discuss about what we will be doing on these analysis. So the purpose of doing all those analysis is to make the system stable. So if we have any control system, then that should be stable. Otherwise, if that the system will be not stable, then we will be not getting the proper output on the output of the system. So that's why all those modeling and all those analysis we will be doing to get the stable, like to get the stable system. So these time, like if you look into after these topics, we have time domain, router bits, and root locus, Bode plot, Euler plot, and Nyquist plot. These things we will be doing to check the stability of a system, like how much stable this system is. So all those analysis we will be doing to check the stability of the system. So let us go first with the time response of the system. So suppose let us have we have some kind of control system with us. So in the time domain response, we will be checking the response of the system, like checking the response means checking the output. So if you give some input to the system, then if you check the output into the time domain, then it is known as a time domain response. So time domain response is much more realistic than the frequency domain response. As we have talked, there is a certain relation between the time domain response and the frequency domain response, which is correlated by the Laplace transform. So the time domain response is more realistic than the frequency domain response, because in the time domain response, you can directly trace out the output of the system. So if you have some like idea of the time domain response, then you will get to know, like we can in the time domain response, we will be having the exact tracing of the output. So the time domain response which will be discussed over here is like discussing about the behavior of the output when we give some kind of input. So there will be we will be discussing some kind of test signal also, like by which we will be applying to that system to checking the output of the system. So we will be discussing about some kind of test signal, under which we will be discussing the step input signal, the impulse input signal, maybe some kind of parabolic input signal or ramp input signal. So these four signal, one is the impulse input, second one is a step input, third one is a ramp input, and sometimes we will be using the parabolic input signal as a test signal for checking the input output relation for the system. So in the time domain response, we will be simply discussing about the first order and the second order system, because after that, like order of the system is mainly depending upon the number of the energy storing element which is presented into the control system. So these things we will be discussing like deeply into the structure of this control system course. So these like time domain response we will be discussing only for the first order system and the second order system. So we will be giving some kind of input to the system and we will be checking for the output. So in the time domain response, we will be having different kind of responses like over damp, under damp, and critically damped, sometimes undamped response. So these responses will be coming like covered under the time domain response. So this is kind of responses which we are getting when we apply some input to their system depending upon the system characteristic. So after the time domain response, we will be discussing in this course, we will there will be some route service criterion by which we can check the stability of a control system. So route service criterion is simply to find out the number of poles which will be on the left half of the S plane and which will be on the right half of the S plane. So by this route service criterion, it is a very powerful tool by which we can get to know about the absolute stability of a system, whether the system is unstable or whether the system is stable. We can get this the route service criterion. So if you talk about this route service criterion, if you have some kind of transfer function, then you can have a direct idea about the how many poles are in the right hand side or how many poles are in the left hand side by this route service criterion. So this is a very important tool by which you can direct like easily get the stability of the system. But this gives you the absolute stability, not the relative, like relative stability. Like if you have two systems which is there for the comparison and you want to compare the stability of the system, like which system is more stable, then you can't compare it by the route service criterion. You can get only the idea of the whether the system is stable or not. You can get the idea of relative stability by this route service criterion. So after that, the route service criterion, we will be plotting the route locus technique. So there it is a plot of that control system in which we will be plotting the like the path of the poles of the system in the root locus technique. So we will be like we will be having some kind of system and we will be having some poles. So we will be having also there some kind of gain. So we will be varying that gain parameter of the system and we will be plotting the poles of the system on a complex plane. So in the route locus technique, we will be plotting the roots of that numerator and the denominator of the transfer function in the root locus technique. So first what we will be doing in this root locus technique, we will be plotting the pole zero plot of the transfer function. And after that, what we will be doing, we will be plotting this root locus technique. So there will be some kind of rules and regulations for plotting the root locus techniques, which is covered under the this root locus technique. And after that root locus technique, there will be another sequence like this root locus technique is also covered under the time domain response. And after this time domain response, there will be the frequency domain response, which will in which we will be varying the frequency and getting the response of the system. So this is the like I have told you, like there will be two such kind of responses. One is the time domain response, and other is the frequency domain response. So the time domain response is covered by this time response and the root locus technique, and the frequency domain response will be covered by this Bode plot, polar plot, and the Nyquist plot. So there will be three more plots will be there in the frequency domain response. One is the Bode plot, second one is the polar plot, and third one is the Nyquist plot. There is another plot which is covered under this, which is known as the Nicholas pulse. So sometime we also discussed that plot also there. So if we talk about the Bode plot, so in the Bode plot, we will be plotting the uh, phase response and the magnitude response of the system. Like if you have some system, you give some input and you will be getting some output, and you have some frequency component into the input. So for that, you have to give some kind of sinusoidal input to the system to get the frequency domain response. So if you give some kind of sinusoidal input, which is having the varying frequency, then you will be getting, let us suppose you will be getting some output. So when you vary the frequency of the input, then you will be getting some varying frequency output also. And magnitude of the output also changes as per the variation in the frequency. So as per that variation, we will be plotting the various frequency domain responses, which is known as the Bode plot, polar plot, and the Nyquist plot. So if we talk about the Bode plot, then in Bode plot, we will be plotting the magnitude of the system, magnitude response of the system with respect to logarithmic frequency, and the phase of the system with respect to logarithmic frequency. So we have to, if we have some kind of transfer function and we in any numerical, we have to plot the Bode plot, then what you will be doing, you will be plotting the magnitude response of the that transfer function and the phase response of that transfer function. That is known as the Bode plot. So there will be some kind of rules and set up rules for that to plot the Bode plot. So that all those things will be discussed under the Bode plot. So in the Bode plot numericals, you are asked to plot the Bode plot response of the transfer function, and sometimes you may ask to find out the gain margin and the phase margin. If you talk about the gain margin and the phase margin, then these gain margin and phase margin are known as a these are the parameter to check the stability of the system, like how much gain margin, like if you have some gain margin for the system, so this represent like this much gain. If you increase for that system, then the system will be on the verge of the stability. After that, if you increase the gain of the system more than that, then you will be getting the unstable system. So these gain margin and phase margin also can be calculated by the this Bode plot. And after this Bode plot, we will be discussing about there is another plot which is covered under the frequency domain response, which is known as the polar plot and the Nyquist plot. So polar plot, it is also plotted on the complex plane, which is known as the GSHS plane. So what we will be doing into the polar plot, we will be varying the frequency and we will be plotting the response of the phase and the gain and the magnitude and the phase response of the system on the same plot. In the Bode plot, we are plotting the magnitude and the phase response on the different plot. In the polar plot and the Nyquist plot, we will be plotting the phase and the magnitude response on the same plot, which is represented by GSHS plot. So in the polar plot and the Nyquist plot, we can also check the stability of the system by these two plots. So there is a Nyquist stability criterion by which we can directly check out the stability of the system. So there will be also some kind of set of rules to check the to draw the polar and the Nyquist plot. So there is a relation between the polar and Nyquist plots, which will be discussed under this chapter. And after this frequency response, like in this frequency response chapter, you have to mainly numerical which is like to plot these frequency response, like you have to plot the Bode plot or polar plot on the Nyquist plot, and by that you have to calculate some kind of phase margin, gain margin. Sometimes you have to find out the stability of the system. So after this frequency response, we move towards the controller design. So controller design is a result oriented thing. So these things, time domain response and the frequency domain response, we are doing to check the stability and how much stable is the system. So this controller design is a design thing, as the name suggests that it is the design of that controller, which we have discussed here. So you have to you have some kind of system and you have to find out the control, you have to design a controller for that the performance of this complete control system improved. So in that, we will be discussing about the controller design. So we have lots of kind of controller like proportional controller, integrate I controller and D controller. So in the P controller, like P controller is known as the proportional controller and I controller is known as the integral controller and D controller is known as the derivative controller. So if we add any two of these, or you can add any three of these, then you will be getting different kind of controller like PI controller, PID controller, or PD controller. So on the basis of the requirement, you will be using these controllers. So these controller will be having certain property like by which you can improve the steady state or transient state performance. So on the basis of your requirement, you can use this kind of controller. So along after this controller design, you may have some kind of like state space analysis also there in the control system, which is covered under the control system. So we all these design and all those things we are doing on the transfer function model, which is transfer function. I have told you it is the simple input output relation of a control system. So this is on the basis of the transfer function model. So there is another modeling of that control system, which is known as the state space modeling. So this state modeling in the transfer function model, we have taken we have take the initial condition as a zero. So if we don't have such kind of strict condition, then we have some kind of this state space analysis in which we will try to find out the input output relation. So sometimes this is also covered under the control system analysis. So by that we can like if you discuss about the under this state space analysis, then we have some kind of state space modeling of any control system, and there will be some kind of stable like observability and the controllability test of the state space model. So it is also covered under the state space modeling. So this is all about this control system course, which is the linear control. So in this one, everything will be the linear control system. So this is under most of the undergraduate course covered with this content only. So on the postgraduate level, you may have some kind of non-linear control, which we will be discussing in the separate module. So in this one, this is the like topics which is covered under the general control system curriculum. So you may have some lots of kind of numerical like block diagram reduction, Laplace transform, and this time domain response and root locus technique and Bode, Polar, and Nyquist. So there will be lots of kind of numerical which you will be getting under this control system course. So let us move toward the time domain response. If you look into the time domains response of a control system consists of the two parts. So I have told you, like in the starting, you will be getting the transient response, and in after that you will be getting the steady state response. So this is kind of like time domain response you will be getting in this time response analysis. So let us see some kind of numerical which is covered under the time domain response. So you can see like this is the kind of second order system which will be covering under the time domain response. So this is the simply the second order standard second order system which is represented by this equation, and this is the our control system which is having this kind of transfer function. So you have to like in some numerical you have to ask to find out the value of omega n, that is natural frequency, and this zeta. So zeta will be depending on the nature of the like control system, and you have to find out these values. So you have to compare these equation and you have to find out the value of this like parameter which will be there in the control system. So you can see like you can say there you can find out the value of omega n and zeta by comparison of these two, and these are the condition by which you can determine like the system is overdamped or underdamped or undamped or the critically damped. So if you have the zeta is greater than 1, then you will be getting the system as the overdamped system. If you will be getting the zeta as 0 to 1, then you will be getting it as the underdamped. And if you will be getting the zeta as 0, then you will be getting it as a undamped. And for the critically damped system, you will be getting the zeta as a 1. So these are the things which are covered under the time domain response. So there will be some more kind of like the terms which will be there in the time domain response, which is known as the like rise time, peak time, and the maximum overshoot and the settling time. So you these are the parameter which can be directly concluded from the transfer function model of the second order system. So you can directly find out the rise time, peak time, and all those maximum overshoot and the text settling time from that. So if you have such kind of system, then you can find out the various responses for the any kind of input. So this is all about the general control system course. So if you want any kind of help regarding the control system on the undergraduate and the postgraduate level, then we will be there for helping you for on any assignment or anything you need help on any subject, then we are here to help you. We are from the your own teacher community, and you can reach to us on this contact. You can reach to us, and we will be very happy to help us on your any kind of project or doubt clearing session. That's all for this module. We will be meeting on the next module. Thank you.